Hi, thank you for watching the talk, Almost Isometric Embeddings of Riemannian Manifolds with the Kernels of the Connection Laplacian. The talk consists of four parts, and I'm gonna combine the lesser two parts into one video, so it'll be three videos in total. The first part of the talk will discuss what's the manifold learning problem and how it can be formulated as the embedding problem in differential geometry. Yet, not all methods from differential geometry are feasible for the purpose of machine learning or data analysis. So let's first look at what it means by high-dimensional data. High-dimensional data are a collection of points in a high-dimensional Euclidean space. For example, an average iPhone photo has size 1600 by 1200 pixels. Let's say it's grayscale, so it's a black and white image. Then what does it mean? Um, you will need 600 times 1200 numbers to describe the color intensity for each pixel. So for each image, you will need roughly 2 million numbers to describe this photo. So if we're seeing this photo as a point in a Euclidean space, then it's a point sitting inside in a almost 2 million dimensional space. Okay. Um, let's say here we have a total example of 15 images. So therefore, I'm gonna see this 15 images as 15 points in a high-dimensional Euclidean space. Okay, and when we have a collection of data um, for machine learning purpose, meaning like you're not just randomly gather a bunch of information and you say you want to analyze this data set. It's like, oh, you have a reason why you are interested in this piece of data set. So sometimes known, sometimes believed. So it is often believed that a high-dimensional data set collected for machine learning purpose can be well approximated by a low-dimensional manifold. For example, a circle or a sphere or something else. Now the point is, um, even when you know there's a manifold structure within the data set, you don't really know what that manifold is. Okay? So how do we analyze a data set under this manifold hypothesis assumption? It's called the manifold learning problem. How do we reveal the geometry? How do we extract the geometric information? Okay, so now let's look at the toy example more closely. Now these photos are being rearranged, and if you look at this closely from top left to lower right, then you can see there's one underlying parameter that's controlling these images. That is the rotation angle of the toy track, right? Okay, so then you can think this um, set of images, they actually have a one-dimensional uh, manifold structure, and you can say it's part of a circle or a circle if you want to. But these images here you see they are not being rearranged by human. It's done by a computer using an algorithm called the diffusion map. So when you have a promising machine learning algorithm, what it will do is it will reveal the hidden information from the geometry, and sometimes it reorganize the data so that you can see what's happening there, and then you have more to say about the data set that you have. So this is a very big problem, and there are many little problems falling under this manifold learning problem. Okay, so in general, this is called the manifold learning problem. It's the problem that we're interested. Okay, so how do we formulate this manifold learning problem using the math language? So one way to formulate it is, let's ask, is it possible to embed a manifold that's sitting in a high-dimensional Euclidean space into a finite dimensional Euclidean space so that we have a bunch of desired properties. Here I'm not listing all the properties, I'm just listing two. So for example, if we have q being less than p, then we drop the dimensionality. So this is called dimensionality reduction. And when you create such an embedding, you don't want the distance being too distorted, right? So you are hoping that embedding would be by Lipschitz, or even better, you want it to be isometric or as close to isometric as possible, right? Okay. So if now we look at this mathematical formulation, then you'd be like, this sounds familiar. Isn't this the embedding problem in differential geometry? Yes, it is. So the embedding problem has been answered positively in the realm of differential geometry. And it goes way, way, way back. It is an ancient old problem. So I'm gonna just start with Whitney. So in 1944, Whitney proved that yes, you can always embed a manifold into a Euclidean space. And later, Nash used Nash-Moser iteration to improve the result. Not only you can achieve an embedding, you can make it isometric as well. But the techniques they use for creating the embeddings is not feasible for data analysis. So let's fast forward to 1994. Barada, Basin, and Galard, in their breakthrough paper, where they use spectral information to create an embedding and put a manifold into a Euclidean space. This method is actually very good for data analysis, but as you can see here, the result they prove is saying a manifold can be embedded into the sequence space, so it's an infinite dimensional space with all eigenfunctions of the Laplace Beltrami operator. So we're hoping that we want the dimension to be finite, not like a sequence space L2, right? Okay, and later it is shown that finite dimensional embeddings are possible, can be done, right? So we have here, I just list a few papers. Again, it's not like all the literature. I'm just listing some important ones that that I use more for my result. Okay. So here we have Bates proof that, so Bates use the Peter Jones. I misspelled the I'm sorry, I misspelled the name. So Peter Jones, Maggioni, and Schultz as result. So he proved that any closed n-dimensional Riemannian manifold can be embedded by a map constructed from kernels, that is by Lipschitz. And Portuguese result showed that he used a different technique, showed that not only this embedding can be made by Lipschitz, you can actually make it as close to an isometry as possible. Okay? And for different application purposes, Amit Singer and Houghton, they developed an algorithm called vector diffusion map, which has its continuous counterpart as the connection Laplacian. So they're using spectral information of the connection Laplacian to do an embedding of a data set. Okay, but here I meant like quote unquote embedding. It's not like the actual embedding yet. But then later, Professor Wu and I proved that any closed n-dimensional manifold can be embedded using eigenvector fields of the connection Laplacian. And for today's result, I'd like to show that we can also have embeddings constructed from kernels of the connection Laplacian, and these embeddings can be made close to an isometry. So that's what we're gonna see.